Hello everyone. Welcome back to week 2, lecture 4. In this lecture, we will discuss how to quantitatively describe fracture behavior of the materials. There are 3 learning objectives. We will understand how we characterize materials fracture mechanics by understanding the 3 critical parameters, including crack size and the geometry, stress level, and the fracture toughness. First, I would like to acknowledge few pioneers who have done the foundation work for developing fracture mechanics before we get into the detailed physics and the mathematics. Bai in 1913, he is considered one of the pioneers who studied fracture mechanics, and the most body of the work was developed in World War I by a British aeronautic engineer, Dr. Arnold Griffiths. So Griffiths completed his PhD thesis in 1910 in understanding the fracture materials behavior of fracture materials. And he's mainly developed brittle materials and energy concept. He was motivated by the contradictory phenomenon. Why is the theoretical strength so much different than the real strength? It's generally theoretical strength of the material, it's way higher than the real strength. So we'll discuss that in the details. And Orwin in 1945 expanded the Griffith theory from brittle material into plastic region. In this case, he talked about plastic constraints at a sharp notch raised the yield strength by the factor of 3, and which may allow the yield stress to exceed the fracture strength. And fracture mechanics was fully developed by Irving in 1950s. He worked for the US Navy and motivated by the World War II US Navy Liberty ship accident. So many US ship was cracking apart during World War II due to the poor quality of the build and the low temperature, which caused the ductile material to transition into brittle. So he further developed the Griffith material theory and expanded that into ductile fracture and using energy release rate concept, which we'll discuss in this lecture. Arnold Griffith, is really considered the true pioneer who first officially started fracture mechanics behavior as a discipline. He finished his PhD thesis in 1910. He worked in the UK as an aeronautic engineer. He was really inspired by why the theoretical stress of atomic bond of a glass is about 10,000 megapascal, where the stress needed to break a bulk glass is only about 100 megapascal. So therefore, he studied this and he published the paper. An interesting part is on the brief note, he was added to the paper stating there's no correction to the paper was needed, since only order of magnitude agreement was of importance. Let's begin to discuss the physics of fracture mechanics by discuss the Griffith hypothesis. So Griffiths asking this question, why the same material, a smaller size typically is stronger than a bulker material. In other words, if it's the same material, we can make an elephant or make a size as small as a mouse. Which one is stronger? So Griffiths was really motivated by this contradictory facts. The experimental stress needed to break a bulk glass, such as a 60 micron or even bigger, is smaller. So for instance, a 60 micron bulk strength of the glass is 170 megapascal. However, the theoretical stress of atomic bonds of the glass is about 10,000 megapascal. So this is a theoretical theory of break a glass bonds, silicon dioxide, atomic bonds. So if this is a silicon, this is oxygen, silicon, break these bonds is need to 10,000 megapascal, which is almost 100 times bigger than the stress needed to break a bulk material. As now we know, the glass fiber has way higher tensile stress than bulk glass. So this is very interesting. The theoretical stress of a material going to a smaller size actually is harder to break than the bulk material. Why is that? So Griffiths look at it from materials' atomic structure. So if we have a perfect material, therefore you have a perfect bonding between the atoms. So as such, when you apply a loading condition, particular tension or extension of material, this tensile loading can be transferred through this atomic bond. Once you apply a loading to a certain extent, which is higher than the bonding between the atoms, so then this bond will break. So therefore, the material will break eventually. So if we were looking at from atomic structure level, so we can see we have many layers of the atoms, and then we apply loading uniaxially. So then this load will be uniaxially transferred through the materials. However, if I do have a certain of the bond is broken, what happens is the applied load will transfer passing through this and then will concentrate it in this area. So therefore, the stress concentration will be happening in certain area, which actually on the edge of the defects. So as such, when the material has internal flaw, that the flaw size, which become very important, and also the geometry. That's why we need to use non-destructive testing methods to understand the crack size and the geometry. Why? Because also the fracture, the material will have significant stress concentration in the defects area. And whether the material will break or not, it really depends on material intrinsic ability to resist the fracture, which we call the fracture toughness. So those are three important parameters in fracture mechanics. So to study the material behavior under a loading condition when the material have pre-existing crack, in 1913, Inglis has proposed methods to solve this by looking at the elliptical hole in an infinite plate. So if there is a crack, which we define the size of the crack with 2a, the length and the height of its 2b, and then the elliptical looks like a circle and the cracks. So that will be like this case. And then the material have infinite size. So therefore the sigma far field also we can call it a sigma null applied in the materials surrounding. So if you're looking at in this case, the geometry of the crack is very important. The sharper of the crack is worse, right? So the radius of the crack. So if I have the crack, so the tip of the crack. So if you blow this up, so here the radius, if we make it bigger, the radius of this curvature of the crack is rho, and then the rho is equal to b squared divided by a. Again, b is the half of the height of the crack, and the a is a half of the length of the crack. The reason it's half because you can think from symmetry standpoint, if you can think of this is actually two of the crack put together. So the sigma local, the stress concentrated at this point at the tip of the crack should be equal to sigma far field, the loading, sigma null, applied on the material times 1 plus 2 A over B. Or we can rewrite this into the sigma null 1 plus 2 A over rho. Again, rho is the radius of the crack curvature. As you can see, the sharper the crack goes, the curvature, the radius of the curvature is smaller, the crack is getting sharper, then the stress will be magnified higher, so it will be higher concentrated. So if the crack is very, very sharp, so the rho is very small, in this case, 1 is very insignificant compared to this number, to 2 A over the rho. So therefore, sigma far field, it should be equal to 2 A over rho. We call that it's a K factor. K is the stress concentration factor. K is equal to sigma local divided by sigma null or sigma far field. That equal to 2 square root of the half of the crack size, the crack length divided by the radius of the crack curvature. So the K is also called the stress concentration factor. That means how many times this stress far field has been magnified at the tip of the crack. That is the most sensitive region. So therefore, the stress concentration factor is to study at what consideration, at what loading condition the stress will become very unstable. So what happens if the very, very, very sharp crack exists? That means the rho is become approaching to 0. So therefore, K approaching to infinity. So from a physics standpoint, we understand. However, from a mechanics standpoint, it's very hard to calculate. So therefore, there is another study method. It's called the stress intensity factor. So stress intensity factor is very different than stress concentration factor. So the stress intensity factor is to looking at the stress analysis around the crack in an infinite plate. That means there's no boundary condition for the stress. So in this case, we can rewrite the equation sigma when theta equal to 0. So it means the crack in this direction. Here is a crack tip. That equal to Kc divided by square root 2 pi r. Kc is called the stress intensity factor. Or K critical. And the Ki is the stress concentration factor. So those are the very two different concepts. So as discussed, we will look at Kc, right? Kc is a stress intensity factor. So C is the stress critical intensity factor. It means when that value reach to the critical points or when the crack become critical or the length of the crack has been grown substantially, so it's become critical. Or specifically, we were looking at the one type of the stress intensity factor called K1C. So K1C is a plane stress intensity factor. So there is a three type of mode of the stress crack opening. One is just the stress open under the normal stress, the tensile loading. Or you have a sliding effect, which is mode 2, the shear or tearing, right? So you have this opening, sliding. So this is the mode 3 for tearing. So in this case, in this class, we will only focus on K1C, which is the most common stress opening case for many materials and structures. So looking at the K1C, I want to introduce a concept. It's called fracture toughness. So fracture toughness is a material property describe the material's behavior at the tip of the crack where the stress become critical stress. K1C is the stress intensity factor, also known as a fracture toughness. So one is the opening mode, one, and the C is a critical. So K1C is also called stress intensity factor. So when the K smaller than K1C, it's safe. But if it's bigger than K1C, the K value is bigger than K1C, is the unsafe design. So how we determine the C is K, we can use the sigma times the pi and then the half of the length of the crack, square root. So K1C is a material property, has unusual units, is megapascal square root of the. So in this case, as we can see, K1C equal to sigma C critical square root of the pi. A is a half of the length of the crack if the crack is in the middle. If the crack is in the edge, so that should be the length of the crack times F geometry factor. So sigma C should be equal to sigma times F geometry factor. So sigma C is the sigma at critical point. The crack will become very unstable. That equal to your far field of the sigma times your geometry factor. Geometry factor is where this crack is located. It's definitely have importance, right? If we consider this as an infinity plate, if the crack is located in the middle and we apply 1.0, if the crack is on the edge, clearly it will be more severe. So therefore your F geometry factor will become 1.12. That's for simplified version. In our class, we'll use this. And actually, if in real engineering design, as you can see, there is the book of the tables for numerous geometry based on Tadin and Irwin's design in 1973. This can be a very complicated geometry factor. So using the stress, crack size, and the material toughness, the design is called the flaw-tolerant design. So in this case, if we look at the stress strain curve, so you have a material going through the linear elastic behavior, and then reach plateau, and then go to the plastic region, and then you have a sigma F, and then sigma ultimate stress, or sigma yield. And this is your ultimate stress, or we call it strength of the material. As we can see, typically sigma C is way smaller than your sigma ultimate, because in this case, we consider this is continuous material. There is no discontinuity, no defects. However, if I have a defect, when the flaw size is getting bigger, and then you have this what we call fracture toughness curve, and then you have your Kc, which is a critical stress, that should be way smaller than your ultimate strain of the material. So that's what we called the newer design, called flaw tolerant design. In this case, we have pre-considered the existing fracture or the existing defects in the material. In this case, we're using the K1C as a design parameter rather than your sigma ultimate strength of the material. As we explained, by using the fracture mechanics of flaw-tolerant design approach, as you can see, the sigma critical, which is allowable, the stress applied on the material is way smaller, typically way smaller than the sigma yield stress of the material. So this is a strength criteria. If I look at a strength criteria, maybe the designed allowed stress will be way higher than actual the stress you are allowed to apply it in the material when material have existing defects. With that, I'm going to wrap up this lecture, and coming next is fracture mechanics behavior 2. We will continue our discussion in this topic.